This video will give you an introduction to Riemann sum, and this is a part 1 of the video. After the introduction, we'll give you a simple example. Consider a typical continuous function y, a function of f of x, on a closed interval from a to b. As shown in the diagram, we are going to define a partition on the closed interval from a to b. It consists of subintervals x0 to x1, x1 to x2, x2 to x3, and typical k subinterval will be xk minus 1 to xk, and the last subinterval will be xn minus 1 to xn, where x0 is a, xn is b. Then the width of the first subinterval is called delta x1. It is equal to x1 minus x0. The width of the second subinterval, we call it delta x2. It is equal to x2 minus x1. And the width of the k subinterval, we'll denote this by delta xk, and it is equal to xk minus xk minus 1. After defining the partition on the closed interval from a to b, we are ready to define what is a Riemann sum. For each subinterval in the partition, we select a point in each subinterval. So, for example, in the first subinterval, I'm going to select a point here called x1 star. To the second subinterval, I select another point x2 star. We continue this process. So on the I interval, I select a point xi star. And the last interval, from xn minus 1 to xn, I select a point xn star. And then from this x1 star, x2 star, all the way to xn star, I evaluate the y. The first y value here is f of x1 star. Then on the point x2 star, I evaluate the y. I find that this y here is f of x2 star. Now in the I subinterval, this y value here is equal to f of xi star. And on the last subinterval, the y value here is equal to f of xn star. The Riemann sum of this function on the closed interval from a to b is the summation of f of xi star times delta xi for I equal to 1 to n. Note that f of xi star delta xi is actually the area of I rectangle. The Riemann sum is equal to net sine area of the rectangle formed as shown in the graph. Notice that the final partitions create collection of rectangles with thinner bases that approximate the region between the graph of f and the x-axis with increasing accuracy. For example, you can see that in the diagram in part B, the partition is finer. The rectangle approximates the region is with much accuracy. The value of x1 star, x2 star, x3 star, and so on can be chosen arbitrarily within the subinterval. Unfortunately, this means that different people may have different value of a Riemann sum because they choose different x1 star, x2 star, and x3 star. In practice, they are chosen systematically. The common choices are the left endpoint of each subinterval, or the right endpoint of each subinterval, or the midpoint of each subinterval. I'm going to illustrate this by using the left endpoint first. The example is use a left endpoint approximation of the area under the curve y equal to 9 minus x squared on the interval from 0 to 3 with n equal to 10 subintervals with equal width. The following is a graph of y equal to 9 minus x squared on the interval from 0 to 3. So I'm going to subdivide the closed interval from 0 to 3 into 10 equal parts. So each part, the width will be 0.3. And the width will be like this. First interval is from 0 to 0.3. Second interval is from 0.3 to 0.6. Third interval is from 0.6 to 0.9. Fourth interval is from 0.9 to 1.2. Fifth interval is from 1.2 to 1.5. Sixth interval is from 1.5 to 1.8. Seventh interval is from 1.8 to 2.1. And then 8 interval is from 2.1 to 2.4. 9 interval is from 2.4 to 2.7. And then the 10 interval is 2.7 to 3. Now, since we are going to choose xi star as a left endpoint, so on the first interval, the left endpoint is x equal to 0. And from there, we find the corresponding value of y, and the y is equal to 9. And we draw a rectangle with height equal to 9 by using a left endpoint. And the height is 9. Then on the second interval, the left endpoint is 0.3. When x equal to 0.3, the value of y is equal to 8.91. So we draw this rectangle, the height is 8.91. On the third interval, the left endpoint is 0.6. When x equals to 0.6, the corresponding value of y is 8.64. So we draw a rectangle with the height 8.64. So this is 8.64 for the height. And then we can continue this process. On the fourth interval, the left endpoint is 0.9. And when x equals to 0.9, the height is 8.19. So we're going to draw a rectangle, height equals 8.19. Continue this process to form the rest of the rectangle using a left endpoint. And then on the ninth rectangle, x equals to 2.4, y will be 3.24. On the 10th rectangle, when x equals to 2.7, y equals to 1.71. After we have constructed this rectangle, we can find the area of this rectangle. That will be the Riemann sum by using left endpoint. So this will be summation of f of xi star delta xi using left endpoint. Xi star is xi minus 1, and because delta xi is 0.3 is the width of each interval, so this can be written as 0.3 times the sum from I from 1 to 10 f of xi minus 1. So summing up from I equal to 1 to 10, you have 0.3 times f of x0 plus f of x1 and so on until f of x9. And you can find this value on the table here. The first value is f of x0, then f of x1, f of x2, and the second last value is f of x9 and f of x10. And when we do a calculation, we have this 19.305. Now I'm going to show you a Java applet. You can find the Java applet in the following website. And this is how the applet works. Question or function I have is 9 minus x squared. And then I'm going to enter the interval from 0 to 3. And I'm going to show the graph from y equal to minus 1 to y equal to 10. as I set the limit. The number interval I'm going to set as 10. And I use the left endpoint as my xi star. So I press compute. So I have 10 interval, the Riemann sum 19.305. Now what happens if I set number interval to be 50? Compute. The Riemann sum become 18.2862, and you find that this Riemann sum is actually decreasing, smaller than the previous value, because this is a better approximation of the region under the curve and above the x-axis. Now what happens if I set the interval to 500 and then compute? Then the sum becomes 18.0269. Let's try to increase it to say 3000. Compute. This is 18.0044995. As you can see that if a partition gets finer, then the rectangles approximate the area under the curve and above the x-axis with more accuracy. What about the midpoint approximation or right endpoint approximation? You can watch the introduction to Riemann Sum Part 2 in the next video.